Good morning, ladies and gentlemen. Take a stab at this question. A 4.55 meter ladder is leaning against a wall with a base, with its base 1.4 meters out from the wall. What angle does it make with the floor?
Pause this, make a diagram, do it your own bad self.
Okay. 4.55 meters. And it's 1.4 meters away. And what angle does it make with the floor? This is the floor, that's the ladder.
What part of the triangles do we know?
This is the adjacent, this is the hypotenuse.
SOHCAHTOA.
SOHCAHTOA, cosine, -1, 4.55 divided by 1.40. And I get, my calculator's over here, cosine -1, inverse cosine, I always say cosine -1. 4.55 divided by 1.
Okay, that's what the calculators say.
Oh. Let me do that again. Let's do that again. 4.55 divided by 1.4. Boom. Oh.
What'd you get?
It's saying domain error.
Here, hit.
Oh, you want to know wrong?
Huh.
Adjacent over hypotenuse. Switch these. 1.40, 4.55. There you go.
Hey, we never make mistakes.
Domain error, that means that there's something wrong with your
It's the calculator's fault.
1.4 divided by 4.55. And we get, there we go, 72 degrees.
So the angle is 72 degrees.
Right.
Is that what y'all got?
Hope so. Okay. 68 kilograms of Miss Moore climbs from the floor of this ladder to a rung which is 3 meters up the ladder.
Oh.
Okay, what can we know? What can we calculate?
Better make another diagram.
Yeah, so this one was the whole ladder is 4.5.
She ain't climbing all the way to the top of that thing.
I did not climb all the way to the top. So now we're only climbing 3 meters. So from here to here is 3 meters.
But the angle's still the same.
And also, this is still the same.
Yeah.
Okay.
What can we know?
What can we know? What can we calculate? Well, let's read our question. I know the mass of Miss Moore. If I know the mass of me, I can also know the force of me.
Force of gravity act on your weight.
Yeah, yes.
You better put a G after that F, girl.
Oh, we're here.
Yep.
Oh, sorry, guys. And then, what can we know? Could we calculate this?
How high above the floor? That's pretty important, isn't it?
Yeah.
I'd say so.
Yeah, and so if we wanted to calculate this, we could do this a couple different ways. Let's go ahead. What side of the triangle is this?
That's the opposite side.
The opposite. So we could say, so we know the sine of theta equals opposite over hypotenuse. So the hypotenuse times the sine of the angle is going to give me the opposite side.
Yes, it do.
And this was 72.
Yep.
Okay, so 3 times the sine of 72, that would get me my delta y, okay? So I would get this, I have this, I have my force of gravity. What can we calculate?
What can we calculate?
Well, we know that work equals force times the displacement, right?
Yep.
Could we do something there? We've got the force, we would have the displacement, we could calculate that.
You could get the gravitational potential energy too.
I could get the UG. Okay, because UG equals mg delta H. Okay.
Wait a minute. Aren't
Same
those the same thing?
Isn't this the same thing, right?
That is.
Anything else? That's good, right?
That's good.
Okay. All right. The law of conservation of energy. Definition.
The most important ideas in all of science.
Energy can be neither created nor destroyed, only changed from one form to another.
How many different kinds of energy are there?
There are a lot of different types of energy. Electrical energy, we got solar energy, we got wind energy.
You got thermal energy.
We got thermal energy.
Nuclear energy.
Nuclear energy, we're learning about that in my chemistry class right now. So there's lots of different types of energies. To simplify, we are going to only consider mechanical energy.
Mo simple, mo better.
The total energy, when we're thinking only about mechanical energy, is going to be the kinetic energy plus the potential energy.
That's right. Keep things simple.
Which simplifies to this. The conservation of mechanical energy, technically, for a closed, isolated system, the total mechanical energy is constant. Whatever we have here is going to equal whatever we have here, and start at the end.
Simple.
Simple.
Profound.
Some conservative forces. Conservative forces are things like gravity, springs, electrical and magnetic forces. Non-conservative forces, which complicate things for us, are things like friction and air resistance.
Yeah.
So when we think about these things, we are going to, as we move forward with this energy unit, we are going to ignore friction and air resistance because they complicate things.
Anytime there's friction, you get heat.
Yes, and same with air resistance.
And with air resistance, you got to push all those air molecules out of the way. You lose some of the energy. That's where they're non-conservative.
Yeah, so we're gonna ignore those, pretend like they don't exist. Okay.
So here's a basic statement.
The beginning of our pyramid. Okay, this is our basic statement. The conservation of mechanical energy. The initial energy is going to equal the final energy.
And you should always start off with that.
Always, always, always. Whenever you have a question that talks about energy, this is where we start.
Things get complicated soon enough. For example.
For our next trick, so we said that the energy total equals kinetic energy plus potential energy.
Yep.
So over here, this plus this equals over here, this plus this.
Yep.
Same thing, but this one's initial, and these ones are final.
This is the second step that you should take because it makes things simpler because a lot of times there'll be at least one of these that are zero.
And then you can just get rid of it altogether.
That's right. Before you get to...
But this is familiar stuff, right? This is 1/2 mv squared, mgh, 1/2 mv squared, mgh. And we have f here for final, but oftentimes we'll just put a little line here for prime.
We can, yeah.
Okay. They're the same thing on both sides because they're equal.
Yeah. So this is a pyramid, and you should put this in your notes. Pause it if you need to get this in your notes.
Okay. Moving right along. Miss Moore has 2,400 joules of UG, potential energy, at her position on the ladder. If she falls, how much K will she have kinetic energy just before she hits the ground?
Perish the thought.
Let's go ahead and start with our equation. So energy in the beginning equals the energy at the end.
Yep.
We know that kinetic energy in the beginning plus the potential energy equals the kinetic energy plus the energy in the end. Okay.
So
now,
when she's up on the top, she's on the ladder. Does she have any kinetic energy?
negatory.
Nope.
Okay, so that one gets to go away. And then how about when I'm at, at the very bottom, do I have any more potential energy up there?
Well, here's the thing. You get to say where potential energy is zero. Where would be a good place for that?
Let's make it right here.
So the floor is zero potential energy.
Equals 0. And that's what we were talking about in our lesson yesterday. You get to choose the reference frame. So that means that at the bottom, I had 0.
That's 0.
Okay, so what this really means is my potential energy at the beginning is going to equal my kinetic energy at the very end. So if I had this many joules of energy at the beginning, then that means at the end I'm going to have the same amount of joules.
That's right.
Yeah, okay. Dang, that's a lot of joules. Okay, how fast will 60 kilograms more be going just before she hits the ground?
Yeah, I just realized something. That 2,400 joules was using the massive Mr. Blaken.
Oh, that's okay.
So this, it doesn't matter.
It'll be all right. Okay, so my mass is 68. If you say so. No, it is. We calculated it. And we want to know how fast is my speed, my velocity, right? So we know that the change in kinetic energy equals 1/2 mv. This is separate from this. Similar but separate.
Yeah.
Delta v squared. And we want the
We've got the kinetic energy.
velocity. We do. So let's go ahead and do some math. I'm going to multiply by 2. And I'm going to divide by my mass. And squared, so I'm going to take the square root. Can they see this okay? Is that
Yeah,
fine?
yeah.
Okay, so my velocity is going to equal the square root of 2 times my kinetic energy divided by my mass. 2 times
2400.
2400 joules divided by my mass, 68 kilograms. My pen is running out. Okay, so square root of 2 times 2400 divided by 68, and I get 8.4 meters per second. Does that sound like it makes sense?
Yeah, it does.
It's a little fast. We'll roll with it, right? That's a lot of smack there. Okay, so that one's done. Okay, moving on here. Mr. Swatwood throws a 0.5 kilogram ball vertically upward with an initial velocity of 10 meters per second.
How can we memorialize this so that we'll remember it once we get away from this slide?
Let's draw a picture.
I like.
I was like, memorialize it. Okay, so Swatwood throws a ball. So it starts here, and we go up here. Ball's up there. It has a mass of
0.5 kilogram, 0.5.
kilograms. Initial velocity 10 meters per second. All right. So A, what is the change in the ball's kinetic energy between the starting point and the maximum height? Okay, wait. So change in kinetic energy. We have an equation for this.
Well, what happens to the velocity at the maximum height?
Oh, great question. So at the very top, what is my final velocity?
Well, it has to stop at the top.
0 meters per second. Okay, so we had the final velocity here. So it has a change in velocity of 10 meters per second here. And we know that we can use this equation right
So
here.
whatever kinetic energy it's got goes to 0.
Yes. Yes.
So how much kinetic energy does it have at the start?
Okay, let's figure it out. So let's go and plug this in. My mass is 0.5 kilograms times, the change in velocity is just going to be 10 meters per second squared. Okay, so 0.5 times 5 times 10 squared, and I get 200. Oh wait, I did the same thing. I forgot. It's 0.5 times 0.5
Times 100.
times 0.5.
So the kinetic energy at the start is
25 joules.
25 joules.
Okay, so what is the change in the ball's kinetic energy between the starting point and the max height? So at the very beginning, it was 25 joules down here. Joules here. And then, I cannot spell. There we go, 5. And then, what do we know about the kinetic energy at the very top? Well, it's going to be 0
So kinetic energy is 0.
at the top.
So you got work at 25 joules. That should be kinetic
Oh,
energy.
sorry. Kinetic energy at the bottom here is 25 joules. At the top, it's going to be 0 because it's all been converted to...
So the change in kinetic energy is negative 25 joules.
Yeah, I like that. Negative. Okay. All right. Oh, I'm getting hot. What is the change in the ball's potential energy between its starting point and its maximum height?
What's that cool thing you can do about potential energy? You get to set 0 wherever you want it. Where
Yes.
would be a good place to make the potential energy 0?
Ooh, let's let's make the potential energy 0 right here.
Oh, okay.
Yeah. So UG equals 0. Okay, so what is the change in the ball's potential energy between the starting point and the maximum? Should we do the pyramid thing right here so we can demonstrate all the
Well,
stuff?
what happens to the potential energy as it gets higher and higher?
Well, as it goes up, the potential energy is going to increase.
Yes, so that's the opposite of the kinetic energy. I think a pyramid would be good right here.
Okay, so let's go ahead and say energy equals energy right here. We know that the energy is going to be the kinetic energy plus UG, the kinetic energy plus UG here.
What's 0? What can we get rid of?
Okay, at the very bottom, our UG is going to be 0, right? We made that equal to 0.
Get rid of that sucker.
Boom, okay, so we have kinetic energy equals, and over here, my kinetic energy at the top is going to be 0.
That's right.
Okay, and we just said, what is the change in the ball's potential energy between the starting point and the maximum height? Well, we said that at the beginning, it was 25 joules.
Okay.
So at the very end,
It's got to be 25
it's got to
joules,
be
y'all.
25 joules. So again, what is the change in the ball's potential energy between the starting point and the maximum height? It's 25 joules.
Yeah.
That's how much it changes. And the why? Well,
It says ignore air resistance.
Yeah.
Why do we ignore air resistance?
makes things complicated.
Well, it'd slow the ball down.
Yeah. So we don't want to have to calculate that.
Yeah.
Okay. At any instant in the flight, what is the relationship between the ball's kinetic and the potential energies?
Ooh,
Okay, well,
I think it's right there.
yeah, basically at at any instant in the flight, the kinetic energy and the potential energy both have to equal 0. The sum of the two have to equal 0.
Nope, they have
I'm sorry, I have to equal 25.
There you
Sorry,
go.
I'm saying the wrong thing. So yeah, that's all there is to
It's
it.
always going to be 25.
It's in this case, right? Not always.
Right.
It's 25 is more.
In this case, yes. Sorry.
Yes. Okay. Letter D. How much work did Mr. Swartwood do on the ball?
Well, let's see. He threw the ball up, yes?
Yes. So work equals.
Yeah, but work is what's that theorem? It's the,
The work energy theorem. Work changes energy, right?
that's right.
Okay, so work equals
It was a change in energy.
delta, the change in energy. How much work did he do on the ball?
Well, how much kinetic energy did it have when it left his hand?
Well, it had 25 joules of kinetic energy. So that means that if he did 25, if he did 25 joules here, then it has to be he did 25 joules here, right?
That
So how much
makes
work did
sense.
he do?
That's so simple. It's scary.
Yeah, it's really quite simple. This pen is no longer producing black ink the way that I
A
want.
dead soldier.
I'll try this one next. Okay, so how much work? 25 joules. Okay.
Who's that guy?
Mr. Boykin squats and throws a 7.5 kilogram bowling ball straight up. Straight up. His hands are on the ball from 0 to 2 meters above the floor. The ball rises to 3.8 meters.
This is something in his youth Mr. Boykin used to do.
Just last year, right?
We got, yes, we got tape on the wall, 1, 2, 3, 4 meters, and I picked the ball up off the floor, got it up to 2 meters, it left my hand, and then it went up to 3.8 meters.
All the way up there. Okay, so first let's draw a diagram. The question is, what can we know? What can we know? Okay. So the ball is here, and we pick it up.
There's the floor. Yep,
Yeah, floor. Up to here, and this was
2 meters.
2 meters. Okay, so this from here to here, that's 2 meters. Okay, and then it's released and it goes
3.8 meters
That's
total.
1.8 meters right there, right?
Yeah, 2 plus 1.8 is 3.8 meters total.
Okay, and the bowling ball has a mass of 7.5 kilograms.
What can we know?
What can we know?
Well, we've already done one thing. We've put how high above the hands it went.
Yeah.
We got 1.8 meters there. That's
Yeah.
one thing.
So let's take a step back here. He does work during this part, right?
Oh, that's right.
So this is when we do work.
Yes.
And we know work is force times distance. It also equals the change in energy.
Well, what happens to the work that he did?
Well, it gets converted into kinetic energy, right?
So it's got kinetic energy right when it leaves his hands.
All right, so here's gonna be my kinetic energy. Okay, so kinetic, just put kinetic energy here.
Yeah.
And then up top, we've got UG, right? Let's
Yeah,
go.
well, what happens to the kinetic energy on the way up?
So as we go up, it's gonna slow down, right?
Yeah. So what's
So-
going to be the kinetic energy at the top?
This kinetic energy at the top be 0.
Yeah.
Okay, so lots of information here that we know. What do we do with this? What can we calculate from here?
Well, where should we make potential energy 0?
Let's make potential energy 0 right here.
That's a good idea.
Okay, so UG equals 0. Okay, so let's take a look at energy. We're going to talk about this little segment right here when we talk about energy. So, because down here is work, which is it's related but
Yeah.
separate. So, the energy at the beginning, K plus, not E, plus UG equals the kinetic energy at the end plus UG at the end. So at the beginning, UG is equal to 0.
Goes away, and at the top,
Kinetic energy equals 0.
now we don't know the velocity, so we can't find the kinetic. Can we find the potential?
Well, potential energy is mgh, right? Yeah, we can definitely find the UG.
What H would we use?
Well, we would use this H right here, the
I
height
agree.
for this. Okay. So our UG, so let's say kinetic energy, our mgh here, kinetic energy equals.
Well, no,
UG.
we want to find the UG first. Forget about the kinetic energy for now.
No, forget about it. So over here, UG equals my mass is 7.5 kilograms times my gravity, 10 meters per second squared, times my height, 1.8 meters. My UG is going to be 7.5 times 10 times 1.8, and I get 135.
Sounds good to me. 135 joules of potential energy. So at the top, the UG is 135 joules.
Okay, so that means at the bottom we have 0, and that means at the bottom our kinetic energy is going to be also 135
According to the
joules.
law of conservation of energy.
Yeah. Okay.
Sweet.
Okay, so basically right now we just calculated, we said we know that energy at the beginning is the energy total at the end.
Yep.
Our energy at the end, we used our understanding of how the potential energy is 0 at the bottom and kinetic energy is 0 at the top to get this
It
equation.
sure is useful to be able to say where potential energy is equal to 0.
It's
isn't it?
very helpful.
Yeah.
You need to be able to do that.
Yeah.
You got the power.
That's right.
And then we can use mgh to figure out what the UG is, and we know that this equals the kinetic energy at the bottom
Boom
here.
to boom to boom.
Okay. So now, is there anything else we could figure out?
Well, what's that thing you have in the first 2 meters right there?
Well, we said that work is equal to force times resistance, which equals the change. That's a change. Which equals the change in energy.
So the change in energy is 135 joules. That means the work is,
135 joules.
ooh, could we find the force? The average force that was exerted on
Absolutely.
that bowling ball?
Let's see. So work is force times resistance, like we just said right here. And so work divided by distance equals force. My work is this.
135 joules.
And then we're talking about the average force over this distance.
2 meters.
It's going to be 2 meters. What is that, Mr. Boykin?
Half of 13 is 7.5 plus 2. That's going to be around 78 joules.
Shall I check the work?
The human calculator.
135 divided by 2, and I get 67.5.
I never make mistakes.
67.5.
I would have never made it through college without a calculator.
I am literally I'm codependent upon a calculator.
I know.
Okay, so basically we can know a lot of things, which leads us to be able to calculate a lot of things.
You know, I think there's one more
Is there one more thing on
that
here?
we could get out
Oh.
of there. Let's see. So the ball was on the floor, it wasn't moving. He did work through 2 meters and it had kinetic energy when it left his hands. If we know the mass and we know the kinetic energy, what else can we know?
If we know the mass and we know the kinetic energy.
What's that equation for kinetic energy? Aha!
Aha. So could we figure out the velocity of the ball here?
Yeah.
What do we say our equation? Velocity equals the square root of 2k divided by m, right?
Yes, ma'am.
Oh. Okay, so that, my knee's just cracked. 2 times my kinetic energy, my energy is 135. Oh, technically. It's everywhere.
Yeah.
Divided by my mass, which is 7.5 kilograms joules. And let's go ahead and do this. Oh gosh. Square root of 2 times 135 divided by 7.5 gets me, look at that.
6 meters per second.
What a beautiful number.
Amazing.
And that's all, folks.
We can know a lot just from that, huh?
Okay, I think that's it. Oh, what homework are they gonna do?
We'll have to think of something.
Okay.